Hello and welcome to this clip having a look at how to do combined spectroscopic analysis exam questions. It uses a particularly challenging one as an example, so I'll try to make sure I point out the possible pitfalls in the question as we go along to help you navigate your way through it. So, first thing to think about is what do these questions actually test? They basically want to see if you can analyze more than one type of spectrum separately before then starting to cross-reference what the information is telling you to see if the spectral information from one supports the information from another. And then obviously problem solving that whole lot of information so that you can come up with a feasible structure. Sometimes more than one possible structure might be accepted. This is what actual chemists do in real life from university level onwards. Once they've done their synthesis in the lab, they need to confirm the identity of what they've produced. Or they might be doing some forensic work for an outside contractor, for example, and trying to find out what's in a blood sample. So there's a bit of a trick to doing them to enable you to process them without a great deal of stress. The trick is don't try and do everything all at once. There's a lot of information that's going to come at you, so allow yourself the time and space in your mind to just deal with one thing at a time. So it might not necessarily be the 4 categories on the screen. It depends on what the information is provided in the question. So let's look at a question to see what we can do with it. This is the question in its entirety. You can see the information given to you on the left-hand side. You've clearly got some information describing the molecule up at the top. And then we've got the infrared spectrum, which will give you the functional groups and the bonds. We've got a proton NMR spectrum that gives you the hydrogen environments. And we've got a carbon NMR spectrum that gives you the carbon environments. So this is the space that you'd have to write on. And you might be thinking, actually, there's quite a lot of things to talk about. I might talk about my infrared up here. I might talk about my hydrogen NMR down here. But sometimes hydrogen NMR requires a lot of space. So it might be that you don't have enough space to do your carbon NMR spectrum. So you can actually write on the spectra themselves. You could annotate this spectra, for example, and get credit. You could annotate this spectrum here and get credit. It's just whichever part of the analysis you think needs the most space, perhaps allocate that to the answer space. There's obviously space at the back of the paper as well. You'll have what's called additional answer space that you might want to use in a question like this. So let's look at how we might process. So we'll start with the question blurb at the top, and I've made it a little bit bigger up here. So it tells you that there are 2 possible structures for deoxyribose, and it tells you that compound B is a structural isomer of deoxyribose. So the reason they gave you the structures of deoxyribose is to allow you to see that there could be a ring structure or a straight chain structure. So not to throw out the possibility of a ring structure. I'm not suggesting that it is a ring structure, the compound we're looking for, but if they give you 2 different structures, it allows you to consider different ways in which the atoms could all fit together. So the molecular formula is C5H10O4. So that means compound B has the same molecular formula, but different structural formula to deoxyribose. So let's now do the infrared spectrum. So this time I'm going to take this part of the question and put this up here. So you can see that you've got several peaks, but it's important to consider what the peaks mean. What are the significant ones? So something you might not have considered quite a lot before, if you're doing A-level particularly, is what does this part on the y-axis mean? Obviously, you'll be using the x-axis quite a lot because you're going to relate these wave numbers to these down here on your data sheet. So this y-axis refers to something called transmittance. So what that transmittance means is the amount of infrared energy that's managed to make it through the molecule to the other side. So the molecule is bombarded by infrared energy. Some of the bonds will absorb that and release the rest of the energy to allow it to go through. So what the machine picks up is how much energy makes it through the sample to the other side. So if we think about it, the greater the transmittance, the shorter the peak and the less significant it is. So this peak here is not very interesting because most of the energy has actually gone all the way through. It's about 70% transmittance or 80% transmittance. But this peak here, relatively small amount of energy has made it through, and that means it's absorbed most of it. That means that's a bond of interest because it's vibrating. Same over here. And interestingly, same over here. This is the one I'm going to just focus on because this is in a place called the fingerprint region, this area here. This is quite a significant peak. So it might be worth thinking about what this one might mean in terms of these wave numbers down here, and therefore in terms of what bonds you might have. So let's do this one first, at 3000. So there's several different options. So we've got C single bond H, we've got O single bond H for carboxylic acids, or we've got O single bond H for alcohols. They all fall into roughly where this is. So we need to look a bit closer to confirm that, to try and work out which one it might be. So I'm going to go for CH bond. I might be thinking, why? Why not maybe OH or something like that? Because that sits between 2,500 and 3,300, doesn't it? But it also says it's very broad, so let's explore what that really means. Looking at the width, that's actually quite narrow. That's from about 2850 to 3,100, much closer to this one here, which is the CH bond. So I'm going to cross the carboxylic acid one out. I'm going to cross the alcohols one out. And I'm just going to show you what an OH stretch shape for alcohols looks like. So it's got quite a distinct kind of shape like that. It's broader than this one. If we do the same for carboxylic acid, you can see it's broader still. That's why it says very broad. So clearly this one here has a different shape to this one here, even though they sit roughly in the same place. So that's what confirms it as a CH bond. Now we've also got this one here. So you can see in the little picture I've got, it's replicated in the spectrum from the question. So that's a C double bond O. So let's just color code it so you can see which one we're talking about. So we're talking about this one here. So it's got aldehydes, ketones, carboxylic acids, esters, and amides. An organic compound, that could be anything. So that's not terribly informative. So we might need to dig a little bit deeper in this one. So remember I mentioned one over here. I'm going to talk about that now. So first of all, let's think about what we don't have to worry about. We don't have to worry about alcohols. We don't have to worry about carboxylic acid. So that sort of narrows down the possible range of molecules that this might be. So let's look at C single bond O. Now that's one that comes up in esters as well. So you can see alcohols, esters, carboxylic acids. We've already eliminated carboxylic acids and alcohols. So we now have a fairly strong case for this actually being an ester. So let's move on to our hydrogen NMR spectrum. So I've parked the information I've worked out here so we can start to build up a picture. This is what I meant earlier by talking about annotating the spectrum. There's nothing to stop you doing this and getting credit because you've shown the examiner that you know what each of those peaks mean using the data sheet provided. So on the hydrogen NMR spectrum, the best thing to do is to actually label the peaks. And there's different ways of writing down the information, but I quite like using the table method, which allows you to process each peak separately and individually. So peak A is around 3.4 on the chemical shift scale. The environment is H bonded to C, single bonded to O. It's a singlet, which means there's no adjacent protons, but this here means there's 6 in that environment. So you've got to think quite carefully about how you're going to pack 6 hydrogens into an environment that where a carbon is bonded to an oxygen. The problem we've got is that the carbon only has 4 bonds, and That means only 3 hydrogens can be stuck on there. But what if there was 2 of them? In other words, 2 separate oxygens, each having a CH3 attached to them. They would both contribute to the same peak if that was the same environment. So they might be in the same place. That oxygen has a spare bond, doesn't it? Because it takes 2 bonds. So that whole group there could be doubled and then 2 of them put on the same carbon. So this is actually quite a hinge point in the analysis because that's an unusual arrangement for HCO. So let's come back to that a bit later. We've got B, which is again HCO, again a singlet, again no adjacent protons. So that is your straightforward H3CO. You've also got HCO here, so the same environment all the way through, singlets again, only one in that environment, so that's going to be HCO. So I haven't changed that from there to there because my RPA suggests there's only one hydrogen in that environment. So looking at the sections of the data sheet, I've put them next to each of the peaks. We can discount chlorine or bromine because it's not in the molecular formula. So now we can start thinking about why do we have several examples of the same peak containing oxygen? It's because we have 4 oxygen atoms, which gives us the freedom to consider that. So it might be that one of these is part of an ester group. That's what was being suggested up here. And it might be that 1 or 2 of them are not. But bit by bit, we're starting to piece together something that might work. So let's see what the carbon NMR spectrum tells us. So again, I've done a little scribble onto my NMR spectrum just to put the information I worked out on the page, so I'm not having to try and hold it in my head and remember it later. But it's a case of laying out all the bits of information that you've got, a bit like a jigsaw puzzle, and trying to piece them into a molecule. So I've put the NMR chemical shifts down the bottom, and what we can have a look at again is labeling the peaks. You could do a table for this if you wished. So A and B both sit in the C single bond O category, which is kind of supporting quite strongly what we're thinking about up here. And D sits strongly in the ester category, which is what we were talking about when we did the infrared. So you can now see how they start to support each other. The further you go, one starts to click with another. Now, yeah, we do have one that's a bit problematic. So what's going on at 100 parts per million? So there's a danger here that this could sort of lead you down a dead end. You might start getting a bit over anxious about, oh, what's going on here? I've got to work this out before going any further. Well, let's see if we can do that without working it out. You can also give yourself permission to not think about something if it's easier to keep you moving on. Because remember, this is actually quite a hard question, like I said. I'm going to provide the examiner's report in a minute so you can see for yourself what they thought when it was actually a live question on A level. So let's pull something else from the carbon NMR spectrum. It's 4 peaks, so there's 4 environments. It's 5 carbon atoms from the molecular formula, so 2 of them must be in the same environment. Now, what did we come up with a minute ago? 2 of these perhaps in the same environment? So there's a bit of cross-linking going on quite regularly now. So we're now in a position to start to pull it all together. So that's our molecular formula. Let's see what we know so far. We know it's possibly an ester, but it didn't come up in the hydrogen NMR spectrum. It came from the infrared spectrum. It might have extra CO bonds elsewhere in the molecule. There seems to be some suggestion that there's other C single bond O groups, not just the ester group. Now we do need to use up 4 oxygens, and the ester only allows us to use up 2, so that is still on the table. There's 2 methyl groups attached to a C single bond O. We've already considered that. It has 5 carbon atoms spread across 4 environments, and then points 3 and 4 might support each other in that case. So let's start with our ester because that's familiar and build it up from there. Don't try and start at the difficult and unusual part because it'll be hard to think it through. Start with something that you know. So let's put a CH3 over there. And now this is where this methyl group bonded to an oxygen comes in. So it's quite unusual. This is called an ether, this functional group. We have a carbon and an oxygen, then a carbon. You won't have come across this in an A-level course, so this is why this is quite a challenging question. But you need to have your mind open to any structure that's legitimate. So legitimate means, do the carbons have 4 bonds? Do the oxygens have 2 bonds? And do the hydrogens have 1 bond? Well, they do in this case. So let's think about why this particular structure might work. Firstly, it allows for all the singlets. So if you look at all of the hydrogen environments, there are no adjacent hydrogens neighbouring them. So therefore they're all singlets. There's no doublets or triplets or anything like that. It has 4 carbon environments, 1, 2, 3, and 4 there. But it's got 5 carbon atoms, 1, 2, 3, 4, 5. The unusual part of the structure is supported by the hydrogen NMR singlet with a relative peak area of 9. So this here equates to this large peak on the NMR spectrum. It also has an ester functional group, which is supported by all of this here, particularly C double bond O, no OH, and C single bond O. So that points very strongly as an ester. So let's have a look at what markscheme has in it and what the examiners thought. So some of the things we've just talked about are spread through these bullet points here. You don't have to say every single thing to get 6 marks, but this is the range of things that they want you to talk about. So the key things to take from this, the question proved to be very challenging. It was targeted to be of high demand. It was meant to be difficult. Most candidates correctly identified the presence of a C double bond O. So there are gateways into starting to get marks that should be accessible for most people. There are 4 carbon environments. That's an example of such a gateway statement. And the structure that you're allowed to use is also here. This is another version that might work. So notice this is our ester, but this has an aldehyde and then a COCH3. This is a bit different to R1. So R1 is this one. Okay, hopefully this has been a useful roundup of how to do this kind of question. Thanks for sticking with it. It's a bit longer, this video, than normal. So thanks for listening again, and until next time, see you soon.